So we're going to take a look at first how the temperature changes have effects upon Haber's process, and how Haber was able to design his factory in such a way to increase the percentage yield or the production of the ammonia that it needed so desperately for providing this population to feed itself through fertilizers. All right, so let's talk about what an exothermic reaction means. The word exothermic, exo means outside, and therm means heat. So the heat is going to be outside of the system. Okay? So we have two options here. We can increase the temperature and we can decrease the temperature. And so this is what Haber did to figure out how to increase that at H3 over there. Now, first of all, because the definition of exothermic means heat going to the outside, if you were to increase the temperature, that means then that this reaction going to the right, and remember, even though this is a double layer with two reactions, the delta H value only refers to the right reaction. Okay? So when we look at the right reaction, we know that the left reaction going from 2H3 to N2 plus 3H2 is an endothermic reaction. The value is positive 25 kilojoules. Exactly the same reaction going the opposite direction, so the subtractions will change. Delta means final minus beginning of the bond energy within it, and so when you reverse it, then it's going to switch around. And that's going to be the same numbers, only in different orders of subtraction, and that would be a positive 25 kilojoules. So the opposite reaction is endothermic. So we don't look at left and right initially when we talk about increasing temperature. We looked at shifting in terms of what the heat is doing. So if you increase the temperature here, that is not going to be favorable to the exothermic reaction. Now, like I said, the reverse reaction is endothermic. So let's take a look at what endothermic means. Endo, like what's the word I was looking for? I had in my head. I want to say the endodermis, but I don't think that's the correct way of putting it. But the inside part of your skin is what I was trying to find. I thought it was endodermis, but that's biology. I'm not really strong at that. But this means inside or toward the inside. And therm, of course, means heat. So the heat is going within the system. Now, if you increase the temperature then that means it's going to favor, increase the temperature, it's going to favor the endothermic direction. Notice I didn't say left or right. I just say I'm going to go in the endothermic direction, whichever one that is. So once I've established that when you increase the temperature, it's going to favor the endothermic direction, then that means that it's going to shift that way, to the left. He did not want that. He wanted it shifted to the right. He wanted to shift favorably to the exothermic direction. And that's where decreasing temperature comes in, because an exothermic reaction will thrive off a lack of heat, and so decreasing the temperature favors the exothermic direction. So the exothermic direction is what we want, because because this is an exothermic reaction. Then we're going to decrease the temperature here. And that's what he did. He ran his reactions at under 100 degrees below 0 Celsius. Okay? So, that's another part of the Haber process. He was able to increase the reduction by decreasing the temperature within the reaction room where this was taking place. Or I should say room is a chamber, basically, a very thick steel chamber which this reaction is run. Okay? So let's take a look at an example here. We have this problem number 69 in your textbook on page 687. And we have this reaction, and this is again an exothermic reaction. It says increased temperature creates one shift. Well, if you increase temperature, it's going to favor the endothermic reaction. If it favors the endothermic reaction, if the reaction to the right is the exothermic, then the reaction to the left favors the endothermic reaction, and so it's going to shift left. Now, what happens to the value K when that happens? If it shifts left, the value K then, that means you're going to have more products, so a bigger denominator, less reactants, smaller numerator, and that means it's going to decrease the value of Kc. Over in the previous situation where I was talking about Haber's process, he decreased the temperature so that he could favor the exothermic direction, which means that he was basically shifting it to the right. So it isn't a matter of endothermic or exothermic in terms of what happens to K, it's a matter of which direction is going to shift the equation. Now, because he's shifting to the right, you're now getting a bigger value of products, which is your numerator, and a smaller value of reactants, which is your denominator, and that means that EA will, not EA, I'm sorry, another part of chemistry. Yeah. But Kc will increase. So that's temperature. Pressure. In the case of pressure, we are now going to use something that we did in Chem 1, and that is deal with Boyle's law. Now, Boyle's law stated that when you increase the pressure of a gaseous system, the volume is going to decrease. It's like if you were to squeeze a syringe that had air in it or some gas, it'll go in the more pressure you put in. So if you decrease the pressure, it'll go out. And the videos that I sent with that last year showed these two guys from Canada sticking their balloons in hot water and in a freezer, and they showed that the balloons expanded in the hot water and shriveled up in the freezer. That is Boyle's law. As pressure increases, volume decreases, or pressure decreases, volume increases. And so it will shift accordingly. So we have to look at the coefficients. So let's take a look at that scenario. Oh, well, let's go back over here, sorry. Let's go back to Haber's process. In the case of Haber's process, I'll put the reaction back here. N2 gas plus 3H2 gas, double arrow, 2NH3 gas. Now, again, remember, you wanted to increase the amount of fertilizer, basically. So what we can do is we look at the coefficients. Now remember, the coefficients actually talk about three different things: molecules, moles, and volumes of gas. So So if we look at the coefficients on the left side, we have 4. On the right side, we have 2. So if we want to shift towards the side of smaller volume, we're going to have to increase pressure, because as you increase pressure, you get lower volume. So increase pressure shift to lower volume. And likewise, if you decrease the pressure, you're going to shift to the higher volume because of the inverse relationship between pressure and volume. Well, Haber, or Haber I should say, I've been saying Haber for years, and I just learned it's actually pronounced Haber. I've probably teaching it for about 150 years. Good on me. Anyway, so you have 4 over here, you have 2 over here, and he wants more of this stuff over here, so he has to increase the pressure. So when you increase the pressure, it's going to shift to the right, and so he had it at like between 50 and 100 atmospheres of pressure, which is phenomenally high. Okay, so let's take a look at a couple more examples. In this reaction right here, increased pressure causes what shift? Well, we have 3 gases on the left, we have 3 gases on the right, and they're even. So, because there is no difference in the pressure between the 2 sides, there will be no shift. Now, in part C of problem 67, it says, same thing, which increased pressure is going to cause what to happen? Well, this is a solid. We don't even take that into account. We look only at the gases. So we got 1 on the left, 2 on the right. We got lower on the left. Increase the pressure is going to shift towards the lower volume. So that means it's going to shift left. And there's your answer. And because of that, because it's going to the left, more denominator, less numerator, AC will decrease. Okay? Let's do one more quick one. Number 73, we have this reaction right here. How can you increase the production of NO? So we have this NO over here, we want more. We got, first of all, one thing we can do is we can siphon off, say, the water, or the steam there. We can siphon off the steam. That's going to allow this to shift to the left. So, number 1 is siphon off both NO and H2O. And it'll keep shifting to the left. Number 2, we look at it from an exothermic and endothermic point of view. This is an exothermic reaction. We want the reaction to shift towards the NO. And so that means we want then, because that's an exothermic reaction, we want to decrease the temperature. Okay, and then finally, we want to increase the NO in terms of pressure. We have 9 on the left, 10 on the right. That means it's going to want a decrease in pressure, so we decrease pressure. And that's how they all work. Practice problems. $66, $74 even. Do not do number 72. Have fun.